Okay, it's 8:30, so let's go ahead and get started today, everybody. Good morning. How's everybody doing today? Good, hopefully. It's cold, which is nice. When I was growing up, I used to really like warm weather just because it was nice to play outside. But now that I'm old and don't play outside as much, the cold weather is nice to just because it makes sleeping at night a little bit easier. Okay, so the plan for today is we're going to finish up our lecture notes on potential flow. So I have an example that I want to do today, and then just some other things that we're going to do at the end. And then hopefully we're going to have some time to do Navier-Stokes today. So probably we're going to start, I'm hoping to start those lecture notes and then finish them up on Wednesday, okay? And so if you weren't here just a couple minutes ago, someone noticed that I posted another set of lecture notes on Canvas on potential flow. And so you'll see that if you look into the files, you'll see that those are notes 07A. And so all those notes are basically it's just one additional example with potential flow, because we're going to do one example right now, but if you wanted to see one more example of how these problems usually go, that 07A will give you another example just to kind of help you out with the homework. Okay. So I know I posted homework last week, so before we get started today, are there any questions on the homework that I can answer? Okay. All right, so let's go ahead and get started. Okay, so where we left off last week was with potential flow. Okay, so we've been doing this for for a couple of lectures. So I just kind of want to just very briefly summarize where we're at. Okay, and so the first step with potential flow, if you remember, we start with the stream function. Okay, and remember, the stream function is basically a scalar function that can be used to obtain the velocity components. Okay. And remember, the one important thing with the stream functions is that it has the property of being linear. And so to get kind of complex flow, what we can do is we can add stream functions together. Okay? And typically, we're going to do this in practice. Okay? Right. And so the example that we kind of started talking about last time was this idea of a half body, which is the combination of a source and uniform flow. Okay. Right, so once you have the stream function, the next step would be just to take derivatives of it in order to obtain the velocity components. Okay. Okay. And so actually, a lot of times you can either do this in Cartesian coordinates or you can do it in polar coordinates. And so, we have both of those, right? And then once you get the velocity components, what you can do is you can take the magnitude of that to get speed. Okay. Okay. And so speed is nothing more than just the magnitude of the velocities. Okay. And then finally, once you have the speed, then one other thing you can do is you can apply Bernoulli and solve for the pressures. Okay. Right. And so, before we jump into an example calculation, I just want to say that all of these things that I've underlined here, velocity, speeds, and pressures, these are not only just velocity and speed and pressure at a single point. These are field quantities where we can get the spatial distribution of velocity and speed and pressure. Okay, and so that's a really powerful thing, because up to this point, with with just straight up Bernoulli or with control volume analysis, we haven't been able to solve for how does pressure vary in like the atmosphere or something like that, or how does speed vary going around an airplane. And with potential flow, we're going to be able to solve for that. Okay. And so just to kind of illustrate this, let's do an example where we have wind blowing over a hill. Okay. Okay. So the geometry looks something like this. Okay. Okay, so you have wind that's coming off this way, and we'll say that this wind has a speed of 40 miles per hour. Okay, and let's define the origin. So let's define the origin to be right here. We'll say that the y direction is that way, x direction is that way. Okay, and let's give this hill a height. And so let's say far away from the kind of far away from the foot of the hill, it has a height of 200 feet. Okay, so that's going to be important. And let's define 3 points in the flow. So let's define this point right here. So point 1 will be kind of somewhere far away in the flatlands. Okay. Point 2 will be kind of this location right here, right above the origin. And then point 3 will be right at the foot of the hill. Okay. And so since we're in English units, let's define the density. So the density is going to be 0.00238 slugs per feet cubed. And so slugs is nothing more than just the English unit for mass. So you can kind of think of it as like a pound mass. Okay. And then one more quantity, we'll define this to be B. Okay. So the length between the origin and the foot of the hill is given by B. Okay. And so remember last time when we went over the half body, you know, that B was an important parameter that we could solve for this. Okay. And so, you know, even though I just said it right now, you know, this hill right here, we can kind of think of this as like a half body, right? And so the way that we can get this geometry from potential flow is if we combine a uniform flow and a source. Okay. And this source is going to be at the origin. Okay. And what this leads to is a half body, which is what we have right here. Okay. And so you compare, if you combine a uniform flow and a source, then you get this kind of body. So if you kind of turn your head like to the side like this, it kind of looks like a parabola. And so that's kind of what a half body looks like. Okay. All right. And so from this problem, we're going to solve for a few things. So we're going to solve for the speed at point 2, and we're going to solve for the height and pressure difference as well. Okay, so I'll write those down on the next page, but are there any questions on just the diagram and the setup for the problem? Okay. Okay. And so now that we have a half body, we know what the stream function is going to look like. So it's going to basically look like what we had in the previous one. Okay. And the nice thing about that is we had already computed formulas for like the speed and the pressures and everything like that. Okay. Okay. So first thing we're going to do is we're going to solve for the flow speed at point 2. Okay. All right. And so if you remember from last time, we had this function for the speed. Okay. Right. So we had speed squared. So remember, speed is just nothing more than just the magnitude of the velocities. So this is equal to big U squared, where big U, remember, is the strength of the uniform flow. And so this big U in this case is going to be 40 miles per hour. Okay, so that's 2 times B over R cosine theta plus B squared over R squared. Okay. Right. And so notice that this is in polar coordinates, right? So it's a function of R and theta. Okay. Right. And so in order to compute the speed, we have to compute what is the R at location 2 and what is the theta. Okay. Okay. So once we have those, we can just simply plug those into the formulas here. Okay. Okay. And so the first thing that's actually easy to do is to find theta, right? So let's start with that. Okay. And so we can see here that point 2 is right above the origin, right? And so it's basically right on top here. So remember, theta in polar coordinates is measured as the angle of a point with respect to the x-axis. Okay, so if you draw kind of an arrow that goes up vertically from the origin up to that point, and so theta is going to be this angle right here. Okay. And so in this case, since our location is just right above the origin, in order to get there, we had to rotate 90 degrees, right? Or in radians, which is what's typically, the unit size typically used for angles, this is pi over 2, okay? And so theta in this case is pi over 2. Okay. And so to get r, we can, now that we know theta, we can plug into the formula for the half-body surface. Okay? So remember, we went over this last time as well. Okay, and so the formula for a half-body surface looks like this. So we have r is equal to b pi minus theta all over sine theta. Okay, we know what theta is because we just solved for it in this case. And so let's go ahead and plug those in right there. Okay, and so we plug those in, and what we get is b times pi minus pi over 2 divided by sine pi over 2. Okay, sine pi over 2 is just 1. And so this we just get b pi over 2. Okay. Right. Okay. And so now we have r and we have theta. Okay. But we have one more unknown that we need to solve for, and that's b, right? And so b, remember, is kind of a measure of it's basically this distance right here in between kind of the stagnation point of the flow and the origin of where the source is coming out. Okay, and so we had one more formula that we can use for b, and we can use the fact that we know the height is 200 feet over here. Okay, right. And so this is another formula that we went over last time. So the height of the half body is equal to pi times b. Okay, and so in this case, b is going to equal to height divided by pi, and the height we know in this case is 200 feet. Okay, very tall hill, and so b is just going to be equal to 200 over pi, right? Okay, and so now that we know theta, we know r, and we know b, we can just simply plug all of those in and solve for u squared. Okay. All right. Any questions on this? Okay. Okay. And so basically we can plug all those into the formula. Okay. And what we get is u is equal to 47.4 miles per hour. Okay. Okay.
What was big U again?
So big U was the speed of the uniform flow. So big U is 40 miles per hour in this case.
Oh, right.
Yeah. Mm-hmm. Yeah. Yeah. So I want you guys to be careful with this because, you know, remember all these formulas that we derived here. So like this one, and this one. So these are only valid for the half body. Okay. So the half body is kind of our very first, you know, complex flow that we're doing. So if I'm going to give you like a flow in the homework which is probably not going to be a half body, then you can't use these formulas. Okay, and so what I want you guys to use instead is, if you look at kind of the process that we use to derive these, especially the speed formula. So that, how we derive a speed formula is important. So if you follow that same process that we did last time, then you can find a speed formula for all different kinds of flows. But this specific speed formula right here is only valid for a half body, where a half body, remember, is just a combination of a uniform flow and a source. Okay? And so any other potential flow situation, you're going to have to not follow this formula, but you have to follow the process in which you use to solve for the speed. Okay, and so that's really important. So for the homeworks, like problem 4 on the homework, I don't want you using this formula because it's not this specific formula right here, because the problem on the homework is not a half body. So it's actually something kind of totally different than everything. Okay. So that's part A. So in part A, we solve for the speed, okay? And so in part B, we want to solve for the pressure difference between point 1 and point 2, okay? Okay. And so anytime you see a question on pressure difference in potential flow, you're going to have to use Bernoulli, right? And so remember in Bernoulli, we have to make our 4 assumptions, but for potential flow, we have those 4 assumptions satisfied, okay? And so let's just simply apply Bernoulli here. Okay. So if we apply Bernoulli, so we can have the Bernoulli sum at point 1, okay? So that's going to be P1 plus 1/2 rho U1 squared plus G Z1 is equal to P2 plus 1/2 rho U2 squared plus G Z2, okay? And so same as before, okay? Right. And so one thing I want to note about using Bernoulli potential flow is that these velocities that you see here, these are the speeds, okay? So so when you plug into Bernoulli here, make sure you plug in the speed, which is the magnitude of the velocities, okay? So don't just plug in like the x component velocity or the y component, make sure you're plugging in speed for these guys, okay? Okay, and so the pressure difference between point 1 and point 2, we can just solve for it to be P1 minus P2, okay, is equal to 1/2 rho U1 squared minus U2 squared, okay? Should be U2 minus U1, sorry. Right? Yes, okay. Plus G Z2 minus Z1, okay? And so we actually have all the quantities here. And so U2 we know because U2 is just what we solved for. So we got this in part A, okay? U1 squared, it's going to be someplace that's far away from the half body. So this is just going to be big U squared, okay? Right? Z1 is just going to be 0 because that's the height of point 1, okay? And then the height of point 2 we can just solve for. It's just going to be r at point 2, which is going to be 100 feet, okay? And so we solved for that actually in part A as well. That was basically the r that we solved for right here, okay? So remember our r was b pi over 2, and since b is 200 over pi, and so b in this case is, or h, or the height of point 1 in this case is going to be 100 feet, okay? Right, so the question is, how come I changed from uppercase U to lowercase u? It's just usually when I do Bernoulli, I kind of do lowercase by default. But you're right, I should use uppercase here because it's for potential flow. Thanks for catching that. Okay. And so once I plug all these in, basically we get P1 minus P2 is equal to 9.31 pounds per feet squared. Okay. And so once you solve for the speeds, then the pressures, you can solve for just by applying Bernoulli. Okay. So remember, the tricky thing is just to make sure you apply speed and not velocities. All right. Any questions on this? Okay. So that example there basically walk you through the process for a potential flow problem. So you're always going to start with the stream function. Either I'm going to give it to you, or you just have to solve for it just by adding some stream functions together. From there, you take the derivatives, you find the velocities, you find the magnitudes, you find the speed, and then you use Bernoulli and find the pressures. So it's pretty systematic. Although sometimes, as you'll probably see from the homework, the math gets a little bit intense. But don't be intimidated by the math. Just make sure you kind of follow this process. And you'll be okay. Okay. And so that's kind of the basics of potential flow. And now I kind of want to go over some situations which have some kind of ramifications for later on. Okay. Specifically, when we do drag and lift kind of later in the semester. Right, question. Oh, U2. So the question is U2. So U2, that is the speed at location 2. Okay. So if we go back to this figure, location 2 was our spot that's kind of right above the origin right here. So U2 is just the speed. U2 squared is the speed squared at the at that location. Yeah. Okay. 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 And so the first case that we're going to look at is flow around a cylinder. Okay. So this is a very classic geometry in fluid mechanics. And actually, if you've never seen an animation of this, it's pretty cool. Okay. Right. Although just by saying it, it doesn't sound that cool. Just because it's just flow around a cylinder. But it is pretty cool. But the interesting thing is that if we're in potential flow, we actually don't see a lot of the cool behavior, which we'll talk about later. Okay, so to get flow around a cylinder, we're basically going to apply the same process as our half body. Is that we're going to add together two stream functions, and in particular, a flow around a cylinder is basically the combination of a uniform flow and a doublet. Okay. Okay. And so the stream function looks something like this. So we have U R sine theta minus K sine theta over R. Okay. Right. And so, usually for our uniform flow, it's just U times Y. But since, the doublet is in polar coordinates, I just kind of switched to that. Okay. Right. And so visually, it looks like this. So you have your cylinder. Okay. Right. So there's our cylinder. And then around the cylinder, we're going to have flow. Okay. So the flow looks like this. Okay. So you can almost think of it as like, a boulder that's in a stream. Okay. So if a boulder that's in a stream, the flow is going to go around it like that. Okay. Okay. And so this cylinder will have a radius A. Okay. And so sometimes it's actually, more convenient to actually rewrite the stream function in terms of A. Okay. Because right now our stream function has this kind of arbitrary strength K, where K, remember, that's the strength of the doublet. But it's a little bit hard to tease out kind of the physical meaning of this. So sometimes, it's easier to write the stream function in terms of the radius. And so I won't go through the derivation, but this is probably the more useful form of the stream function. Okay, so it's gonna be UR 1 minus A squared over R squared. Okay, sine theta. Okay, and so basically, in order to get this equation, what I did was I assumed that the sphere had a radius A, and then you know, I solve for k in terms of a, and this is what we get. Okay? And so this is a little bit more intuitive because here you can just basically plug in directly the physical quantities of the situation. So you can plug in the uniform velocity u, which is usually pretty easy to solve, and you can plug in just the radius of the cylinder a. So this form's a little bit easier to work with because then you don't have to work with some arbitrary k variable. Okay? All right, any questions on this? Okay. Okay. And so just like we've done in the past, we can take the derivatives of this and solve for the velocities. Okay. But of particular interest is actually the velocities on the surface of the cylinder. Okay. Okay. Right. And so let's solve for these velocity components. Okay. And so UR, remember the formula for this is going to be 1 over R d psi d theta. Okay. And then if we want to evaluate this on the cylinder surface, we're going to evaluate this at R is equal to A. Okay. Right. And so basically we're going to take the theta derivative of the previous expression, plug in R is equal to A, and then we get you know, the velocity at the surface. Okay. And then what you'll see from this is that UR is equal to 0. Okay. So in the flow around a cylinder, you know, the UR component, or the velocity that's coming out radially out, is 0, which intuitively makes sense because we have this cylinder right here, which is supposed to be kind of a solid surface. And so if we had any UR at the cylinder surface, that means flow would be penetrating out through the cylinder or coming in. And if that was the case, then we wouldn't have a cylinder. We would have something else. Okay? And so the fact that UR is equal to 0 makes kind of perfect sense in here. Okay. Okay. And so to get u theta, we're going to take the derivative of the stream function with respect to r. Okay. And we're going to take the minus sign of that. Okay. And again, we're going to evaluate this at r is equal to a. Okay. And then once we do that, we get a velocity of minus 2u sine theta. Okay. Right. And so what this tells us is that on the surface of the cylinder, our velocity is just kind of purely rotational. Okay. And so we have flow that's basically going around the cylinder like this. Okay. Right. And so we have no flow penetrating out. We just have flow going around the cylinder. Okay. Okay. And so another thing that we see is that because of this sine theta right here, our velocities are at a maximum when theta is equal to pi over 2 and 3 pi over 2. Okay. Okay. And so these theta locations, they correspond to the top and the bottom of the cylinder. Okay. Okay. And so if you have flow around a cylinder, the places where the velocity is going to be max are like when it's kind of going around the bed. Okay. Which intuitively kind of makes the most sense. Okay. Okay. And so now that we have the velocities, and by token, since UR is equal to 0, we have the speeds, right? So the speed is just going to be U theta in this case. And so from here, we can solve for the pressures. Okay. And so remember, to solve for pressure, we're going to use Bernoulli. Okay. And so I'm going to assume that there's no height difference here. Okay. Okay. And so in Bernoulli, remember, we always have to apply to the 2 different points. So where are these 2 points that I'm considering here? Okay. And so on the right-hand side, I'm considering a point that's on the surface of cylinder. Okay. And so if we're on the surface of the cylinder, the speed is just going to be u theta. So that's what we have here. So we can just plug this guy in right here. Okay. And then on the left-hand side right here, we have this P0 plus 1/2 big U, rho big U squared. And this is going to be somewhere far away from the cylinder. Okay. Right. So it's in a location far, far away. Right. And so if you want to kind of have a visual point, point 0 would be kind of somewhere like over here, except kind of way, way over there. Okay. Okay. And so what we're going to assume about point 0 is that since we haven't hit the cylinder yet, the speed at kind of point 0 far away is just going to be our uniform flow velocity, big U. Okay. And so that's what we plugged in right here. And then we're also going to assume that we know the pressure out there too. Okay. So P0, in all likelihood, this is used to simulate atmospheric flow. And so P0 could be like an ambient atmospheric pressure. Okay. And so we'll assume that we know everything on the left-hand side, and then we're going to solve this equation for P1, where P1 is going to be the pressure on the cylinder surface. Okay. All right. Any questions on this?
Yeah. What was the big U squared and the somewhere far from cylinder again?
Right. So big U squared, that's going to be the velocity of our uniform flow. Okay. And so remember, for the flow around a cylinder, it's the combination of a uniform flow and a doublet. And so uniform flow is just kind of a flow that just kind of goes in just one direction. So big U is just going to be the speed of that uniform flow. Yeah. Okay. Any other questions on just how we got here so far? Okay. All right. So if we plug in everything, we can solve for P1. And so there's going to be a little bit of math here, but I'll leave that to you guys. Okay. And so we get P1 is equal to P naught plus 1/2 rho big U squared 1 minus 4 sine squared theta. Okay. Right. And so what's interesting about this pressure distribution is kind of this last term right here. Okay. Okay. And so what's interesting about this last term is that it's actually a symmetric. Okay. And so from potential flow, what it predicts is that the pressure distribution will be symmetric. Okay. And so what do I mean by that? And so if we make a plot, okay. Right, so on the top, on the y-axis right here, we'll have pressure. So this is P1, okay? And on the y-axis, or on the x-axis here, we have theta, okay? And so at the origin here, it's going to be theta is equal to 0, okay? This might be like theta is equal to, let's say, pi over 4, okay? This is pi over 2, okay? This is 3 pi over 4, okay? And then we'll get to pi, okay? And so what this graph is going to represent is basically the pressure as we go from kind of one side of the cylinder to the other, okay? And so just to kind of, draw a figure here, right? So here's our cylinder. Here's our flow coming towards it, okay? Right. And so if we kind of define this to be kind of the first point, and so pi over 4 would be something like this. And so pi over 4 would be this location on the cylinder right here, okay? Pi over 2 would be this point of the cylinder. So remember, pi over 2 is the top point of the cylinder, okay? 3 pi over 4 would be this one on kind of the back side. And then pi would be the one kind of once you kind of made kind of a full half rotation around the cylinder, okay? And so what we're tracking right here is the pressure as we kind of go from here to here to here to here, okay? And so if we go from one of the horizontal sides of the cylinder all the way to the top, and then on the back side. Okay. And so what this pressure distribution predicts is a pressure distribution that looks like this. So we're going to start high here at pi 0. Okay. Then at pi over 2, we're going to get a minimum. Okay. And then we're going to come back up, you know, back over there. So by the time we kind of reach the other side of the cylinder, what we've said is that the pressure, it fully recovers. Okay. Okay. Right. And so by fully recovered, what it means is that, you know, in order for it to go around the cylinder, and the fact that, remember, the flow speed at the top of the cylinder is really high, right? That in order to reach that top speed, you know, the pressure has to go down, right? Because remember from Bernoulli, pressure and speed are inversely related, right? So if we have high velocity, that means low pressure, okay? And so from this point where the pressure is the lowest, by the time it reaches the back end of the cylinder, we say that the pressure has fully recovered, okay? Okay. And so why is this interesting? So this is interesting because this is not what happens in reality at all. Okay, so if you have flow around a cylinder, then you don't have this full pressure recovery. Okay, because if you do have pressure recovery, if you think about pressure as kind of a way of exerting force, if you have the same pressure on both the front side and the back side of the cylinder, that means there's going to be no net force on your object. Okay, and if no net force, that means there's going to be no drag or no air resistance. Okay, that means, you know, if this were true and the pressure fully recovered, you'd be able to, you know, stand in the middle of the Mississippi River and be basically just like Jesus Christ and just have flow kind of go around you, and you'd feel no drag at all. You just kind of stand there and be like, I'm God. And so obviously, you know, that's not true. Everyone knows that if you stand in the middle of the Mississippi River, you're probably not going to have a good time. So it's going to basically sweep you along. Okay. And so what happens in reality? So what happens in reality looks something like this. Okay. And so in reality, what you have here is you have kind of the same dip in pressure. So, you know, as the flow goes around you, it goes down. Okay. But then once you start going on the back side of the cylinder, the pressure starts to recover a little bit, but eventually just kind of gives up. Okay. And so in the orange right here, what I have is kind of the experimental measurements. Okay. And so this is kind of what happens in reality. So, you know, you have this kind of uneven pressure distribution. And this difference in pressure between kind of the top and the bottom, this is what's known as form drag. Okay. And so we'll go over what form drag means more at the end of the semester, but you can kind of think of form drag as kind of like air resistance. Okay. Okay. And this little kink right here, once the pressure distribution tails off, this is what's known as flow separation. Okay. And so in reality, you know, you're not going to have nice streamlines of what we have here on the bottom. Okay. And so what happens in reality is that the flow is going to come, it's going to hit the object, it's going to start going around. Okay. But at a certain point, you know, it kind of stops following these streamlines. So at a certain point, like right here, and we'll say that right here, okay, the flow kind of breaks off just like this. Okay. Right. And what we say at that point is that the flow separates, and then what you have in here on the back side in between here is what's known as a wake. Okay. All right. And so a wake, you know, we'll go over this much more later. A wake basically has very low pressures. Okay. And so, you know, because of the low pressures in the wake, you have a net force in this direction. Okay. And that's known as drag. Okay. All right. And so if you're interested in aerospace, you know, drag, form drag like this and separation and wakes are very, very bad. Okay. And so if you're designing like an airplane, you know, you want to avoid this at all costs, because if you have separation, you have a wake, that means your plane is stalling, which is very, very bad. And so a lot of times you design your airfoils and you design your airplane wings to kind of make sure that this doesn't happen. Okay. Right. Okay. And so if that's what happens in reality, you know, then why does potential flow predict this kind of full pressure recovery, right? Right. And so the fact that potential flow predicts this full pressure recovery and you have no drag force, this is called D'Alembert's paradox. Okay. And so D'Alembert's paradox basically states that, you know, in potential flow, when you have no viscosity, then there's no drag force. So there's no drag force in potential flow. Okay. And so, you know, it's called a paradox because it's something that, you know, obviously does not make any sense at all, right? And so the thing that, you know, that basically causes this drag is viscosity. Okay, so remember, in potential flow, we're ignoring any kind of viscous effects or any kind of viscosity. And so once you introduce viscosity, then you start to see this realistic behavior of like flow separation and form drag and air resistance. Okay? But since in potential flow we don't have any of that, then we get D'Alembert's paradox, which basically, in plain words, D'Alembert's paradox says that, you know, any object in potential flow experiences no drag. Okay, which is not true. Okay, any questions on this, on D'Alembert's paradox? Okay. All right, so there's one more kind of a neat effect that I want to go over with potential flow. And again, you know, this we'll come back to this once we get to drag and lift. But it's kind of cool to look at just now, okay? Because we have all the mathematics that we can do. And that's this idea of adding spin to create a lift force. Okay. Okay. And so let's take our stream function for flow around a cylinder. Okay. And so our stream function for that was U times R times 1 minus A squared over R squared sine theta. Okay. Right, so here was our kind of our flow around a cylinder. Okay. And then to this, let's add a vortex. Okay. Okay. And so this is our formula here for an ideal vortex. Okay. And so this is a counterclockwise vortex with circulation gamma. Okay. Okay. Right. And so adding a vortex will kind of shift the velocity vectors. Okay. And so if we kind of draw our cylinder, okay. And so our cylinder looks like this. And so remember, in on the previous one, we had flows that kind of goes kind of nicely around the cylinder. But once we add some rotation to this, like that, then our streamlines kind of start to look like this. Okay, it starts to skew the streamlines kind of like the following. Okay. Okay. Right. And so basically what's going to happen is that because we're adding this rotation, on the bottom side of the cylinder here, we're going to have flow that speeds up. Okay. Because if you can imagine, you know, the rotation is going to go counterclockwise. So on the bottom of the cylinder, you know, the vortex is going to add to the potential flow. So we have faster flow down here. Okay. And then on the top side of the cylinder, you know, we're going to get flow that looks like this. Okay. And so on the top side of the cylinder, since the vortex is going counterclockwise, we have the vortex going this way. Okay, it's going to the left, but our uniform flow is going to the right. And so those two are going to kind of interact and cancel each other out. And so on the top side, we have slow flow. Okay. And so what we've added here, basically by adding a rotation, is a little bit of asymmetry. Okay. And so basically, what instead of having kind of, you know, the same speed of the flow above and below the cylinder, by adding the vortex, now we have faster flow in the bottom and slower flow up top. Okay. All right. Okay. And so just like before, we can solve for the velocities and the speeds and the pressures, and the details of that is in the notes. But I do want to go over kind of one kind of special thing, okay? And that's the lift force, okay? But I'll do that on the next page, okay? And so before I get there, are there any questions on this? Okay. Okay. And so we can solve for the pressures here, okay? And if we do that, we get the following, okay? So we can basically solve for the pressures on the cylinder, just like before. Okay, so we have P1 is equal to P naught plus 1/2 rho U squared, 1 minus 4 sine squared theta, okay? And then plus a bunch of other stuff because we have the rotation now. So we have 2 gamma sine pi all over pi AU minus gamma squared over 4 pi squared a squared u squared, okay? And so it's kind of a beast, but the exact expression is not that important, okay? But so what we can do is we can take this pressure and we can solve for the vertical force, okay? Okay. And so the vertical force is given by this formula, okay? So if Fy is equal to minus integral of from 0 to 2 pi, okay? Because we're going to integrate all around the cylinder times P1 sine theta d theta, okay? Sine theta A d theta, okay? So we have to throw in the radius there, right? And so, this is going to be a pretty a doozy of an integral because, we have a lot of terms here, but I'll just kind of skip straight to the result, which is pretty easy, okay? And so we get Fy is equal to minus rho U gamma, okay? And so this is basically a net force downward, okay? Okay. And so since this is a force that's kind of perpendicular to the uniform flow, this is usually characterized as a lift force. Okay. In this case, it's a downward lift force that is going down, but they're all characterized the same. So any force that's generally perpendicular to the flow, in this case, the uniform flow is known as a lift force, okay? Okay, any questions on this? So the math details, are not that important. That's kind of why I skipped over it. But what's important is that I want you guys to know is that if you do add some rotation, you can basically generate a force in the flow. Okay. 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 And so let me draw our cylinder again here, just to kind of illustrate. Right. And so if you remember, once we add rotation, we kind of add this asymmetry. So we have fast flow, okay, and we also have slow flow on top, okay, and that's if we add a counterclockwise vortex, okay. And so what do we know about the relationship between speed and pressure, right? And so since the flow is faster on the bottom, this means low pressure, right? And since the speed is slow on top, this means high pressure. Okay. And so if we have high pressure up top, low pressure on the bottom, okay, this creates a net force going this way. Okay. And that's exactly the force that we that we observe here. Right? And so this is really interesting. So it's interesting just because if you just spin something, you can kind of create a net force that's in the flow, which kind of seems a little bit weird at first, okay? And so what are some applications of this, right? And so believe it or not, this phenomenon of spin and creating force is used a lot in sports, okay? And so who here follows baseball? Dodgers in the World Series? Right?
Yeah.
Yeah, so baseball, there's this whole idea of adding spin to create force is kind of the driving force behind pitching, right? And so if you ever thrown a baseball before, you know that when you pitch the ball, you add spin on it, and that various spins will create different kinds of pitches, like a fastball, curveball, sinker, and stuff like that. Okay, and so the physics behind that is driven by this guy right here. Okay. Right. And so the very best pitchers in baseball, they really know how to control the spin of the ball perfectly, right? I don't think that baseball pitchers have PhDs in fluid mechanics, but they have kind of an intuitive feel about if I spin the ball this way, it's going to create a certain force, right? And the force that or the origin of that force is generated just by this, and that force is basically predicted by potential flow. Okay. And so this phenomenon of adding spin to something in order to create force in a flow, this is known as the Magnus effect. Right? And so baseball is kind of the big thing, or kind of the first thing that comes to mind when you think of this, partially just because Dodgers are in the World Series. But actually a lot of other sports utilize this as well. So football, volleyball, basketball, all these sports, they utilize this spin effect in order to create a force on the ball in order to go in one direction or the other. And even other things too, they apply this Magnus effect well. Right? All right, any last questions on potential flow and the Magnus effect? Okay, so that's it for potential flow. So it's a big set of lecture notes, but there's a lot of really cool applications that you can see. Okay, and just like I mentioned at the beginning of class, I posted an additional example with potential flow. So I'm not going to have enough time to do that in the lecture, but if you go to the website, you should see an additional lecture notes 07A that you can look at, and I think that one's a little bit closer to what I asked you to do on the homework too. So definitely check that out if you need some help. Okay, and so now that we're done with potential flow, we're ready to move on to at least my favorite part of fluid mechanics, which is the Navier-Stokes equations. And so I'm a little bit sad because this class in fluid mechanics is so jam-packed that we kind of have to fly through everything quickly, and Navier-Stokes kind of gets the short end of the stick. So we're only going to spend probably the rest of today and probably Wednesday going over Navier-Stokes. But Navier-Stokes is probably the most important equation in fluid mechanics. It's also the most difficult to solve, kind of by far. So we're not going to be able to solve it, but we will be able to kind of apply it in certain kind of niche situations to solve for certain things. Okay. And so I love Navier-Stokes. I love it so much that I named the Wi-Fi in my apartment Navier-Stokes. And so every time I come home from the apartment, I check my phone and said, "You're now connected to Navier-Stokes." I said, "Yes, I am, both in Wi-Fi and in spirit. I'm connected to Navier-Stokes." Okay, and so what do we use it for? So Navier-Stokes is, the idea behind Navier-Stokes is the same as potential flow, in that we want to solve for the spatial distributions of velocity. Okay, and so potential flow, remember, allowed us to do that. So remember, the way we did that in potential flow was we took a stream function, took the derivatives, and get the velocities, yada, 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 okay? But what was the one thing that potential flow ignored? So potential flow ignored viscosity, okay? And so what Navier-Stokes will allow us to do is it'll allow us to solve for velocities when there's viscosities, okay? Okay. And viscosity is really important. So we've most of the time in this class, we've kind of been ignoring viscosity, but it's actually going to be really important for things like this. Okay. Okay. So where's velocity important? Where's viscosity important? That's kind of the first question that we should ask. Okay. Okay. Or in other words, what are situations, where we need to apply Navier-Stokes versus, potential flow. Okay. And so potential flow is nice because it gives us, a pretty good way to compute velocities and pressures, but it can't be applied everywhere. Okay. And so kind of the first situation, that we can go that we need to use Navier-Stokes is a flow that goes through narrow spaces or narrow channels. Okay. And so you might have, something that looks like this. Okay. So you have flow in a channel. Okay. And so we'll actually solve this flow later. Okay. So you can see here, there's not that much space usually in between those channels. Okay. So viscosity is going to play a big role here. Right. And so another very common situation is you have flow in a pipe. So you have flow that goes through the water pipes in your house or your apartment. Okay. And so viscosity is going to be really important here because the pipe is a relatively small, space. Okay. Right. And so why are these situations kind of big on viscosity? Okay. And so remember, the big thing that viscosity will do is it'll cause fluid to stick to solid boundaries. Okay. Okay. And so if you remember in potential flow, we were ignoring this, right? And so potential flow, like we have flow around a cylinder, what we were assuming that the flow is just going to go right past the cylinder. So the fluid is going to come in, it's going to hit the surface, and then just kind of slip right off. Okay. And so with viscosity, what's going to happen is the flow is going to come in, hit the surface, and then some part of the fluid is going to always stick to the surface. Okay. So not all the fluid, right? So you can't just take your glass of water and turn it upside down and expect it to be a DQ blizzard, right? And so obviously, the fluid flows, but the fluid that's right next to the surface, even sometimes it's just in a very microscopic layer, will stick to that surface. Okay, and that produces actually some really important effects. Okay, that are important to keep in mind. Okay, and the driving force for this is viscosity. Okay. Right. And so when viscosity comes into play and we have this kind of a no slip condition, that's another name for this. Okay. And we have this no slip, potential flow won't allow us to solve for these kind of situations because potential flow basically assumes that the flow is going to slip. Okay. Right. And so basically, we're going to need Navier-Stokes when there's going to be a solid surface and, as you'll see that there's going to be a gradient in velocity. Okay, any questions on this? Okay. Okay. And so now let's actually write out the Navier-Stokes equations, okay? So I'm not going to derive these equations because they're, you'll see why. But I think what's more important is the applications of these equations, which is what we're going to be focusing on. The application and the interpretation, okay? And so I'm gonna do kind of the same thing as kind of when we did Reynolds transport. So I'm gonna write out the entire equation, and then I'm gonna basically tell you, what do each of the terms represent? Because, because ultimately, usually when instructors go through, lengthy derivations and proofs of the equations, what we want you to understand is, where do each of the terms come from, and what do they physically represent? Okay, and I think that's you can achieve that without going over through a very lengthy derivation. Okay. Okay, and so first thing to note that the Navier-Stokes equations are partial differential equations. Okay, and so since partial differential equation is kind of a big mouthful to say all the time, and it happens a lot in applied physics, which is basically what we're doing in engineering. And so we normally shorten this to PDE. Okay, so if you hear the term PDE, all it stands for is a partial differential equation, and that's basically math language for an equation that's basically going to be impossible to solve by hand. Okay, and so these are basically the equations for Navier-Stokes. Okay, so basically Navier-Stokes, you can kind of think of it as just a conservation of mass and momentum. Okay, but we're going to express this conservation of mass and momentum in differential equation form. Okay. Right, so let's start with mass. And so mass is going to be given by the continuity equation. So I think we went through this kind of at the very beginning of last week. Okay. The conservation of mass is going to be given by this. Okay? So conservation of mass is basically going to be the divergence of the velocity field. Right? And so conservation of mass, we basically take partial derivative of u with respect to x, partial derivative of y of v with respect to y, and partial derivative of w with respect to z. Okay, and we just simply add those together and just set those equal to 0. Okay, and so if you remember from early last week, this is called the continuity equation. Okay, and so you'll probably hear me refer to this equation as that. Okay, and so when we're doing examples, probably on Wednesday, and I say continuity equation, this is the equation that I'm referring to. Okay, and so this is kind of part one. So already, we have 3 variables and 3 dimensions. So it already looks a little bit scary, but this isn't even the final form yet, okay? Because we got to go over momentum. Okay? And conservation of momentum is a lot scarier. Right? And so just like in RTT, we're going to have an x component of momentum, a y component, and a z component. And so I'm just going to write out the x component first, and then I'm going to use that to basically explain kind of the different terms. Okay, so this is basically momentum in the x direction. Okay, and so we're going to have this. First, we have an unsteady term. So you have partial derivative of u with respect to t. Okay, then we have okay. Then we have all of these guys. Okay. Then we have one pressure term. Okay, so we have -1 over rho, and so this rho right here, that's a density. Okay, and then the pressure is going to come in the form of a derivative, just like that. Okay. Then we have gravity, right? And so this is a g sub x right here. So this is basically saying the gravity in the x direction. Okay. And you're probably wondering, how can we have gravity in the x direction? This is for cases, actually, like we have in the homeworks, where if you have your coordinate axes that are tilted right here. Okay? And so if your coordinate axes are tilted, then you might have a gravity that goes in the x direction. Okay. And then to this, we're going to add the viscosity term. Okay. So our viscosity term is going to be nu. And so this is nu right here. This is not v. Okay. So this is kinematic viscosity. Okay. It's going to be multiplied by partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared. Okay. And so this is kind of the this is the x component of velocity in Navier-Stokes. Okay. So it's a doozy, right? Right. And so what I'm going to do next, since we didn't derive this equation, is I'm going to basically explain what each of the terms represent. Okay. And so I'm basically going to, the way I'm going to do that is I'm going to box the terms in different colors. Okay. And on the next page, we'll explain what each of the colors represent. Okay. Okay. And so I'm going to group the terms like this. So first we're going to have the term in red, then we're going to have the terms in green, then the blue terms, then the purple term, then the orange term. And on the next term, and on the next page, I'm going to explain what each of these kind of represent. Okay. So it's a long equation and it's big, and I know that, right? And so luckily the lucky thing is that when we're doing problems involving Navier-Stokes, we're not going to solve this entire thing. And so what's going to happen most of the time is we're going to apply assumptions and cancel out a lot of these terms. But the important thing is, I want you guys to kind of see the whole equation, and I want you guys to kind of understand what each of the different terms represent, because each of the terms, they have a physical meaning, and they each represent kind of a fundamental kind of way that, a fundamental mechanism that can affect fluid flow. Okay, and so I think this approach right here is a little bit more intuitive than kind of going through the whole derivation, which let's be honest, is going to take at least one whole class session to derive something like this. Okay, are there any questions on this before we start deriving the terms? No. So the name of my Wi-Fi is Navier-Stokes, but my password, obviously I'm not going to say it. Yeah. Right. Oh, sorry, Danny, I missed your question. So Magnus effect makes objects curve, so that's correct. Yeah. And so Magnus effect is basically if you add spin to an object in flow, like if you throw an object, you add spin to it, it's going to make it curve. That's right. Mm-hmm. Yep. Okay, and so let's start defining each of these terms. Okay. Okay, so first we have the red term, right? So our red term was du dt. Okay. And so we've seen something like this before, and it's it has the same kind of definition as our RTT. And so anything with the time derivative will be an unsteady term. Okay. Right. And so just like in RTT, unsteadiness basically represents any changes that can occur with time. Okay. Okay. It's any changes that can occur in time at a fixed location. Okay. Okay. And so we're gonna do the same thing that we did with RTT, in that basically 99% of the time, at least in this class, we're going to assume that this is 0 under the steady assumption. Okay. And so if you have steady flow, then any time derivatives are going to be 0. Okay. And so that applied with RTT, and this that's going to apply here as well. Okay. Next, we have the green terms, right? And so the green terms are going to be this collection of 3 different terms right here. Okay. And so the green terms, what they represent are these are known as convection terms. And sometimes you'll see them called advection terms as well. Okay, so advection, convection, they are slightly different in reality, but they're basically, they kind of represent the same thing. So if someone says convection, advection, they basically kind of refer to the same thing. Okay, and so if you kind of remember these guys from our material derivative, these represent how the velocities can change in space. Okay. Okay. And so if we want to connect this to basically RTT, you know, this represents basically our inflow outflow terms, right? So remember, our inflow outflow terms represent how, you know, things can be carried along with the flow, right? And so you have a fluid that's flowing, things can be carried along with it. This represents the same kind of thing. So this represents how, you know, fluids, you know, in this case, momentum can be transported with the flow, right? And so, you know, mathematically, you know, these convection terms are actually the most difficult to deal with. And so the reason, you know, the big reason why Navier-Stokes is impossible to solve is actually because of the green gang right here, right? And so the reason for that is because these terms are, we call them nonlinear, because we basically have a velocity times a derivative of velocity. So mathematically, those terms are really, really difficult to deal with, okay? Okay. Right, so those are the green terms. So green terms represent convection. And so the blue terms here, this is our pressure gradient term. Okay. And so what the pressure gradient term represents is how changes in pressure can drive a flow, okay? Or differences in pressure. Okay. And so we already know that flow goes from high pressure to low pressure, and this is basically the derivative way to express that. Okay. All right. And so next we have purple. Okay. And so purple here represents gravity. Okay. Not gravity. Okay. And so gravity, you know, is pretty straightforward. So gravity is just another force that can drive flow. Okay. Right. And so mathematically, you know, gravity is known as a what's called a body force. And so body force, you can kind of think of it as a force that's kind of felt all throughout. And that's just with just by the fact that we're in a gravity field here on Earth. Okay? And so another example of a body force could be like an electromagnetic force. So that's a force that's kind of felt all throughout the body. Okay, so it doesn't act on the surface. Okay? But for fluids, most of the time we're only going to we're just only going to worry about gravity. Okay. Okay. And then finally we have the orange term, which is kind of the new guy. Okay. And so the orange term, what this represents viscous. This represents viscous effects. Okay. And so all the effects of viscosity are kind of encapsulated in this term. Okay. And so you know, we're going to spend, you know, the majority of Wednesday talking about this, but just kind of in a nutshell, what this term basically does is it forces velocity to have smooth variations in space. Okay. Okay. And the big reason for that is because we have that second derivative. Okay. And so mathematically, you know, whenever you have a second derivative like that, that's that's kind of we call it a diffusion term, or has a diffusive effect. Okay. And so the net effect of that is it kind of smooths kind of things out, right? And so we'll go over this a lot more next time, but I just kind of want to give you the viscous term in a nutshell, right? Okay. So any questions on this?
Yeah, real quick with the second term, your green for the convection
Yep.
stuff. You've got the derivative u with respect to the partial derivative with respect to x.
Yep.
And then you've got plus, is that velocity?
Right. So u, v, and w here are those are the components of velocity. So u is the x component, v is the y component, and w is the z component.
Okay, so it's different than your kinematic viscosity and.
Yes.
Okay.
Yeah. So this v right here is velocity. Yeah, with the iPad, it's a little bit hard to write it, but yeah, this v is different from this one over here, where this one is viscosity right here. Yeah. And so this what I've shown you right here is just the x component of Navier-Stokes. So there's also a y and a z component, and so I won't write those out, but they look very similar, except a lot of the u's here, they're going to be replaced with the with the y and the z component. Okay. So we're out of time for today, so I don't want to keep you guys. So once we're going to pick this up on Wednesday, and we're going to see how we can actually solve kind of this monster of an equation right here. Okay. So thank you everybody for tuning in today. I know we covered a lot today, but at this point you should be able to do problem 4 on the homework, and then once we finish Wednesday, then that'll give you everything you need for problem 5. Okay. All right. So hope everyone has a great day today. I have office hours after this if you have any more questions. But besides that, I'll see you guys on Wednesday. Thanks, guys.
Thanks, Professor.
Dr. Tran.
Thanks.
Thanks. Right. Are there any more questions for you guys? Okay. So I'm going to end the call. So if you have any more questions, I have office hours after this. If not, you can email me, message me on Discord, any of that stuff. Okay? So have a great day, everybody.